All right. Okay. Last week we started on acids and bases, chapter 14, and we got up to this point where we were going to start solving acid-base equilibrium problems. So that's where we're picking up. We're going to finish out 14 and chapter 15 today, and we have plenty of time because there's no lab today. But let's see, since you're here, I'm going to hand you a copy. Let's see, that's not it. That's it. So that's what it looks like, Julianne. Okay, that's the one you're looking for.
Okay.
Okay. Print out your own copy. I'm going to talk to somebody about that projector. It needs a little help. Okay. So this topic, calculating the pH of strong acid solutions, actually we're segueing into calculating the pH of weak acid solutions. And to do that, well, we are going to talk about strong acid solutions in the beginning, and that's okay. That's a good way to get our feet wet. But when you're solving an acid-based problem, the first thing you want to ask yourself is, what are the major species that are in solution? Right? Now, this may be before the reaction takes place. In fact, it is before the reaction takes place. And then you allow your major species to react. Some reactions will be completely ludicrous. You'll just X them off immediately. But eventually you whittle them down to, lost my pointer. Eventually you'll whittle them down to major species that actually do undergo some sort of reaction with one another. Then you have to decide which one of the reactions is dominant. And we'll go through that and give you some hints on how to figure that one out. Once you've decided the potential reactions that can take place and which ones are dominant, then you ask yourself, is this reaction one that's going to establish an equilibrium between products and reactants? Or is it one that's essentially going to go to completion? Once you decide which ones are going to completion, those are the ones you want to do first. Get those species reacting to completion, and then what very often happens is the species that are left over after the reaction takes place are the ones that enter into an equilibrium situation. All right, so that's in words. And if necessary, determine what the pH is. And that all depends on the question that's being asked. Okay, so here's an example, which gave you the answer too soon. So if we have an aqueous solution of 2 times 10 to the minus third molar hydrochloric acid, that's very weak. It's a strong acid, but it's a dilute solution. Let's put it that way. Let me use my terminology correctly. What are the major species in this solution? Well, when you put hydrochloric acid in water, what happens to it? It completely dissociates. There's no time to think about, what's going to react, because it immediately dissociates into hydrogen ions, chloride ions. Okay, what else is in there with it? Well, if they're going to be aqueous, that means water is also a major species. Right? So you have those three. So now what's the pH? Well, we know that this reaction is going to completion, right? Say we're going to dissolve that gas in water. And I guess we need water here too. So we have these species and that water. So these are the major species, and the pH is determined by that concentration right there, whatever that happens to be. And what does this depend on? We know that hydrochloric acid is strong, so that means if we put so much in over here, we're going to get all of it over here. We know the concentration then is 2 times 10 to the minus third molar HCl, which means this is also 2 times 10 to the minus third molar. So the pH then is, just by definition, the negative log of 2 times 10 to the minus third, which is 2.7 pH. Okay, that's what you do with a strong acid or a strong base. It essentially goes to completion. There's no equilibrium situation at all. So how about this one? Here we have hydrochloric acid again at a different concentration. So the major species are again these three. There's no HCl remaining. It's gone. It's completely dissociated. And then you just take this concentration because you know that it goes to completion and gives you this concentration equal to the mother molecule, the hydrochloric HCl. And then you just take the negative log of that and you get a pH of 10.8. So is that an acid or a basic solution?
That would be acid. Or no, base.
Base. Anything greater than 7.
Yeah, I was about to say.
Right.
I was thinking that.
Right. Okay. So let's say we add HNO3 to water. What do we know about HNO3? It completely dissociates just like hydrochloric acid. HNO3 is strong, which means complete dissociation. So when it reacts with water, it gives you this hydronium ion plus the nitrate ion. Now this is what actually happens, right? That previous slide where it said hydrogen ions plus chloride ions, that's for convenience. Like I said before, and I'll say it again, protons never exist independent. They always attach to something. So they attach to the water molecule, and this determines the pH, right? So the major species are going to be, let's see, added water reaction takes place immediately. Okay, so we get this one, right? So we know that reaction because it's a strong acid. Then why would we not get the nitrate reacting with water to generate hydroxyls? Look at it this way. So here's our nitric acid plus water gives us the hydronium plus the nitrate. Okay? So what's characteristic of this one? Which one's the acid, which one's the base? There's the acid. Water is acting like a base. It's a proton acceptor. So here's the conjugate acid of that base, and here's the conjugate base of that acid. what do we know? If we know that this acid is strong, what do we know about its conjugate base? Its conjugate base is weak. There she is. All right. Let's see. I haven't handed out the lab for next week. It's going to be a Ka of acetic acid. So I have hard copies here, but what you'll have to do is go on Blackboard and print yourself out a copy so you'll know what's coming next week.
Okay.
I'm gonna mark you present.
The lab view is needed for me, right? Not the last week.
No, the one last week will be due next week.
Okay, yeah, it's in the Dropbox.
Okay, good. All right. So if we know this is a strong acid, that means its conjugate base is weak. So what do we mean by a weak base? A base is a proton acceptor. So that means if it's a weak base, it doesn't want protons, right? It's happy just the way it is. It's not a good acceptor of protons. So now that we know that, this is a weak base. Now we can say something about its potential reactions with water. Okay? If this is a weak base, then it is not going to accept a proton. That's why this reaction does not occur. All right? The next question you have to ask yourself is, well, you have to compare the potential reactions always in aqueous solution to this one, where water reacts with itself, right? And you've got to decide if the controlling reaction is this one or something else. So that's what we want to get to next, is deciding when does the self-ionization of water control the reaction and when does something else control the reaction. Okay, here we go. So here we have another strong acid at a concentration of 1.5 times 10 to the minus 2 molar. The major species would be, since it's completely dissociated, produces protons, nitrates, and water. Do you want to mute or do you want me to mute?
I got it.
Okay. Just remember to unmute if you want to talk. Okay, so those are the major species. That means that since these are the major species, we're not going to get any reverse reactions because this is a strong acid. You'll get this in solution, but the pH is determined solely by that species right there. So that being true, all we have to do is take that concentration here, which is based upon its mother molecule, and take the negative log of it. And that gives us 1.82 pH, which is acidic. Yeah, very acidic. Right? It's like stomach acid, depending on what you just ate. If you eat an Italian meal with lots of tomatoes, it might drop well below that, down closer to 1.
Yeah, I have a problem with that acid reflux.
Yeah. Yeah. Okay. So now we get to weak acid equilibrium problems. You still have to list the major species that are in solution. then you got to find out which one produces the hydrogen ion or the proton, and write the balanced equation that produces that proton. Then you will, since it's a weak acid, there will be an equilibrium constant for it. So if we have the generic acid, right, and let's say it's going to react with water, for instance. Well, actually, both directions, because it's a weak acid, right? Weak acid. So it's going to produce the hydronium. That determines your pH. And the strong base, right? So if this is a weak acid, and that's a strong base, the conjugate base, then which side is the equilibrium going to lie predominantly? Reactant side. It's a weak acid. It doesn't want to give up its proton. That's a strong base. If it's got any protons, it's going to take them. Right? So the equilibrium lies back this way. That means the K with a little a, which means the equilibrium, acid equilibrium constant, is based upon these two species. And sometimes they just write the proton in there. And the strong conjugate base concentration divided by the undissociated acid. Right? Why didn't we put this one in here? Because it's a pure substance, it doesn't count. In aqueous solution, you won't put water in there. So this is the value that you'll get, and whatever that species happen to be. For our lab next week, it'll be the acetate ion, and this will be acetic acid. Okay. So that's the equilibrium that decides the pH. Then that's if this is simply an acid. This is an example of an equilibrium situation for a weak acid. But if we have a weak acid in there perhaps, and we add something else to it, then that reaction may dominate. So that's what we have to decide before we can actually do a calculation. You can't just plug numbers into a formula. That's a recipe for disaster. So we're going to follow that ice table concept, initial, change, equilibrium. And in doing that, we have to know the initial concentrations of the species and then what their changes happen to be. And then we can write the equilibrium expression in terms of the unknown and solve for the unknown. And if the unknown happens to be, if X happens to be this value, then we're good. We got that value right off the bat. If it happens to be some other value, then we have to use it to figure the other ones. And that's what the ice table does, that helps us to do. Most of the time, not all the time, but most of the time, when we have an expression where we're going to have the concentration of this one minus X, right? Because it's going to go from here to here, and we're going to lose some of it. So it's nearly always going to have this concentration minus X. That X is going to be so small because it's a weak acid that we can ignore it. Sometimes we will have to check to be sure it's within the 5% rule, but more often than not, it will be. Okay, so let's consider a real problem where we have this reaction. We're going to make an aqueous solution of hydrocyanic acid, and there's the K value, right? So it's a very weak acid, 10 to the minus 10. And the initial concentration of HCN is this. So what are the major species in solution? Well, it's a weak acid, so we're going to have lots of HCN there. We're going to have lots of water, right? But not so much hydrogen ions or cyanide ions. They're not going to be major species. So those are the two that we're going to react. Well, I already told you that. Because it's a weak acid, you're not going to have these two in significant amounts. They're not major species. So here's what the reaction looks like. HCN plus water yields hydronium ion plus cyanide ion. And the Ka is this. But water also reacts with itself, right? And its K is 10 to the minus 14. Which reaction controls the pH? It's the one that produces the most protons, right? This one only produces protons to the effect of 10 to the minus 14th, whereas this one produces protons 10 to the minus 10th. So it's 4 orders of magnitude greater ability to produce protons. That means this one is the controlling reaction. Okay? All right. Oh, I guess they're not going to let us do a calculation with that one. So we'll have to move on to something else. So let's say we have 0.5 molar aqueous solution of hydrofluoric acid, which is a weak acid. And its K is this, right? So we know right off the bat that that one's going to produce protons or hydronium ions at 10 orders of magnitude more effective than water is. So the controlling reaction is going to be this one, not that one. Okay, so now that we have the controlling reaction set up, we're going to react HF with water, produce the hydronium ion and the fluoride ion. When we start out, we have none of these to speak of. Well, we actually have none of these for sure, but we have very little of these compared to what we're going to generate. That's why this approximate is here. We shouldn't have any fluoride, so that shouldn't be there. But this one, there are some hydroniums there, right, from the dissociation of water, where water reacts with itself. But like I said, it's 10 orders of magnitude weaker than HF. So in the end, it's not going to matter. Right, so we start off with this initial. Now, what we're going to do, we're going to lose a little bit of this one and produce equal amounts of these two because it's 1 to 1 to 1 to 1. So our equilibrium situation is going to be this, that. So if we write our equilibrium for HF, we have hydronium ions, fluoride ions as products, and then HF as our reactant. And all we have to do is fill in the values. So HF is going to be 0.5 minus X. And this is going to be plus X, and this is going to be plus X. Right? So we're going to assume that because the equilibrium constant is 10 to the minus 4th, let's see, where is it? There it is, 7.2 times 10 to the minus 4th. Okay, that the value of X is going to be extremely small. Right? So that's why we're saying this is approximately X squared over 0.5 is equal to 7.2 times 10 to the minus 4. And then we solve for X. and we get X equal to 1.9 times 10 to the minus 2 molar. And let's go back up here and say, what was the question? What's the pH? So X is equal to the hydronium ion concentration. We could use this value to do the negative log of X equals the negative log of this value. And that's pH. And we get a pH of 1.72. Now, if we go in and actually insert the value of X in the true equation, does it give us the Ka that's close to the true Ka, right? So we plug those numbers in, and we get this value, which looks like it's a little high, but is it close enough? And you just, this is the accepted value, so take the calculated value minus the accepted divided by the accepted times 100, and we get 3.9%. So our approximation is correct by the 5% rule. If you want to know the exact value for X, then what you would have to do is keep that X, generate your quadratic equation, and solve it. And you would find out exactly what the X is, and find out that the pH is probably not much different, right? Because these are linear differences, whereas this would be a logarithmic difference. And the logarithmic difference between these two is negligible. Okay, any questions? All right. Now here's a new concept, percent dissociation. What do we mean by percent dissociation? And that was starting to get tired. Let's see, we got another one here. There's a blue. There's another black. Percent dissociation. In words, percent dissociation is how much of your acid ends up on the dissociated side, right, on the product side, relative to how much you started with, right? So that's why the equation says the amount that was dissociated, right? So if we start off with, say, 1 molar concentration of HF, and say 1/10 of it dissociates, right, to produce this and this. So let's say we end up over here with 0.1 molar. Okay. We ratio this to the original. So 0.1 over 1 times 100 would be 10%. Right? So that would be 10% dissociation in this case. Now here's a rule of thumb. I think I've got slides to prove this one. This is a simple calculation, but the percent dissociation, whereas Ka is a constant for a given temperature, right? But percent dissociation is variable. It depends on what you started with. It does depend on this value, but that value is a constant and this one's not. So as we change the initial concentration, we will get a different amount here. Right, if we start off with 1 molar here and get 0.1 here, then what if we back it down to 1/2 molar? Well, we would expect, if this were a constant ratio, 1/2 molar would give us 0.05 molar here. But it doesn't. It gives us more, like 0.06 or 0.07 molar, right? So as you lower the concentration here, the percent dissociation actually goes up. Okay, that's the rule of thumb. Now I just need to prove it. Let's see, is this going to prove it for me? Let me see. I said I was going to prove it. Yeah, eventually, eventually we'll prove it. So we're going to use this example of formic acid, right? That's derived from, formic acid is derived from the genus of ants, Formica. That's because they produce formic acid in their bite. That's one of the reasons it stings so bad. Once they get that acid down there against your nerves, then you feel it. Fire ants are the worst. It's really a cocktail. This is only part. They've got other things in there that, you know, accentuate the pain even more. Okay, so if we start off with a solution of 8 molar formic acid, which is pretty high, and the dissociation is 0.47%. Okay, we're given those facts. Can we determine the Ka for formic acid? In order to do the Ka for formic acid, we need to satisfy these conditions. H2 dissociates into CHO2 minus. Okay? So the Ka is going to be that one divided by this one. Okay? And we want to know what's that value based upon this information. Right? If we know this information is reliable, then we can start off saying, well, start off here, initial, we got none of these, but we know that the dissociation here, the change is going to be a loss of this one to that amount, right? 0.47% in decimals is 0.0047. That's why this and not that is used, right? So 0.0047 times 8 is how much negative, how much was lost here. And since it's a 1-to-1, that's also how much was gained here and here. Okay? So if we do the calculation, we can say this one subtracted from that one gives us this one. So it's not a lot of change there, but we get a small amount of this one and this one. Now that we know those values, we can plug them in here and determine, here we go, and determine our Ka for formic acid, 1.78 times 10 to the minus 4. Okay? So simply knowing the initial concentration and the percent dissociation, we can calculate a Ka value for that acid. Now, calculate the pH of an 8 molar solution of formic acid, right? So what do we still have here? Well, we have that value right there. That determines the pH, right? How do we know that? Because we calculated this value, and that is significantly larger than 10 to the minus 14th for water. So this is the controlling reaction in aqueous solution. And that value right there determines the pH. So that's all we have to do is the negative log of that value, and we find out that the pH is 1.42. So it is quite acid. So, rule of thumb time again. the value of Ka for 4 molar formic acid solution should be what? Higher, lower, or the same? Look at the question. I'm asking, does Ka change? Nope. K is a constant. It doesn't matter what the concentration is. K will always be the same, as long as you don't change the temperature. That's one condition. The value of Ka of an 8 molar formic acid solution. Oh, let's see. It'll be the same as. Okay. The percent ionization, however, varies with concentration. So the percent ionization of a 4 molar formic acid solution should be what? Greater than, higher than, lower than, or the same as an 8 molar formic acid solution, based on our rule of thumb. The dissociation should be higher. The lower the concentration, the higher the percent dissociation. Now the concentration, since we're starting at a lower concentration, the concentration of these species will be lower in the 4 molar. But this is ratioed against that, right? So this might be lower, but it's higher than expected based upon the initial percent dissociation. Right? So it's going to be higher than the 8 molar. Okay, so what am I doing here? Okay, this is a discussion of a Q value. All right. So we have this generic acid, HA. And it dissociates. We don't know how much it dissociates yet, but that is a possible reaction in aqueous solution. So we'd write the Ka for that one as H times A minus divided by HA. Then we look at, compare the value of HA at equilibrium to the initial concentration of HA. That's what the little 0 means. This is what we started with. This is what we end with. So this is going to be the equilibrium situation, and that actually should be parentheses, not brackets. But we stuck the little 0 down there to distinguish the two. This is what we start with. This is equilibrium. So it's equilibrium because we subtracted some of it. But we know that for weak acids, they're basically going to be equal. They're not going to be that much difference between the two. Okay? And the H plus and the A minus are both going to be equal to that X, because whatever disappears here shows up there. All right, so the Ka then would be X squared divided by HA 0, starting for initial conditions. So now what we want to do is, what happens if water is added so that the equilibrium HA becomes 1/10 as strong as before? And the question is not just what happens, but what happens in terms of equilibrium shift. Because if it's at equilibrium and we do something to it, there's a chance that it will respond, according to Le Chatelier. But we want to know which direction is it going. If we dilute that with added water to 1/10 of its original value, which way is it going? Is it going to make more protons, or is it going to make more undissociated acid? Right? So we're creeping up on percent dissociation proof. So here's what it looks like. Before any adjustment happens, the concentration of A minus is equal to the concentration of H plus, and that's equal to X divided by 10, right? Because we've got this here producing that one, actually both ways, there. So we have a concentration of these established, and now their new concentrations, when we add the water to dilute them, the new concentrations are going to be, if this is X and this is X, the new concentrations are going to be 1/10, right? So this is old, this is new, right? This is the disturbance that we've given it. We've gone from there to there. Now, which way is it going to shift? Right? So the concentration of this will also be a 10. Right? So it's going to be an original divided by 10. Okay, so how do we determine the direction of the shift in equilibrium terms? How have we done it in the past? Well, the easiest way is if there's nothing over here, then you know it's going that way. Or if there's nothing over there, you know it's going that way. But if there's some on both sides, we have to do a calculation, right? We have to calculate Q. So if these are the new starting positions, right? Q doesn't have to be equilibrium, right? These are the new values. So it's going to be this one times that one divided by this one. Like that. Okay. So there's our calculated Q right here. And what we find is that we can factor out the 10, the denominator, and the denominator ends up in the, let's see, the denominator is the numerator. So this becomes this, right? Flip it up. That cancels one of them. So now the Q is X divided by this one times 1/10. There's your 1/10, right? I factored out this 1/10 right there. So that leaves, oops, X squared. So it's X squared over this times 10. Q is 1/10 of this value. So what did we determine when Q is, and what is this value? Well, that's the K, right? So if Q is less than K, which way is it going? Well, that way. That means this is less than the K value. You got less of this than you need. So when you dilute it, you're actually driving it that direction. So that's why the percent dissociation increases, right? If we drive the equilibrium that direction by diluting it, then we get, relative to what's in there now, we get a greater amount of this, right? We diluted everything. So the absolute concentrations have gone down. That's true. But the percent dissociation went up because the equilibrium shifted to more of this from that. Okay? All right. So not that I want to make you do that proof on the test, but that explains why percent dissociation goes up as concentration goes down. If you remember that one rule, then you'll be fine. So the pH of formic acid should be higher or lower than the same as the pH of 8 molar formic acid solution. Okay, let's think about it. The percent dissociation goes up, but what actually happened to the hydrogen ion concentration? It went down because we diluted both sides, right? We went from this one, diluted it to that one. Now the pH would be higher than expected based on the dilution, but it's still less than the 8 molar formic acid. That's wrong. Is it wrong? I just contradicted myself. Are we going to prove it? There's 4 molar. Yeah, okay. pH is, oh, duh. What did I just do? I forgot how we calculate pH.
Oh.
The hydrogen ion concentration is lower, right? Which makes the pH higher. So let's do the calculation. The next slide is going to show us that. The hydrogen ion concentration produced is shifts to the right, but the concentration has decreased by adding 10 times more water. So the pH is actually higher. That means it's more basic than 8 molar. Okay, so 8 molar has the lower pH. 4 molar has the higher pH. So we can determine the pH of a 4 molar solution, right? We just run through our calculations and we find that this is the hydrogen ion concentration. We do the negative log. Where is it? I thought we were going to do the, oh, percent ionization. We're going to do that first. Sorry. So this is X, right? So that means this came one to one from here. So that means this divided by that times 100 is your percent dissociation, 0.67 for 4 molar. And what was it for 8 molar? It was 0.47. Yeah, 0.47 for 8 molar, 0.67. Let's see, 0.47, 0.67. This is for 8 molar. This is for 4 molar formic acid. So the percent dissociation, or they're saying percent ionization, which is the same thing, went up for 4 molar. Now what's the pH? Well, we know now that based upon, back up, this, that 4 times X, we need to know what X is. So X turns out to be this value, and our pH is 1.57. And this was 1.4 something, wasn't it? 4.2. Okay? So there's a practical example that gives you the pH for a more dilute solution. So the pH increased, but the percent dissociation, percent increased, percent dissociation increased. This is more acidic than that one. Okay, let's talk about bases. As soon as we finish this chapter, we might take a second or two break. Just see where we're going. Oh, there's more. There's more of this than I expected. We might have to take a sooner break. Okay, go back to our original definitions. Arrhenius said that bases produce hydroxyl ions. Right? Bronsted and Lauer said bases are anything that can accept a proton. So that covers the OH minuses, right? They can accept protons from water. But other things can accept protons, like the ammonia molecule can accept a proton and create ammonium. Okay, so just as a reminder, basic solution, pH is greater than 7. If the compound has hydroxyls in it, as Arrhenius said, then it's usually a strong base. Right? So good examples are lithium, sodium, potassium, calcium hydroxide. All these guys over here. These are definitely strong. These are strong, except that, for instance, calcium hydroxide is only slightly soluble. In water. But the calcium hydroxide that does go into solution completely dissociates. Right? Once it gets in solution, it makes all hydroxyls and all calciums. It's just that calcium hydroxide itself tends to be a solid in water. So how would we calculate the pH of a solution? Well, calculate the pOH. Right? If you know the hydroxyl ion concentration, you can use Sorensen's method, calculate the pOH. And then we found out earlier, I think, that the pH then would be 14 minus pOH. I did show you guys that one, didn't I? So what's the pH of a solution of sodium hydroxide here? Well, sodium hydroxide definitely, at that concentration, will dissociate completely. So you can calculate the pOH of that one, which would be 3, right? Negative log of 10 to the minus 3 is 3. And then 3 from 14 would be 11. So the pH should be 11. Okay? Those are easy to do as long as this coefficient is 1. You can do the rest of it. If it's not 1, yeah, then you have to get your calculator out. So calcium hydroxide, as long as we're given this concentration of calcium hydroxide in solution, then you can ignore its solubility. You can say, okay, that's how much is in solution, all right? So what's the hydroxide concentration? Wait a minute. Sodium hydroxide. Okay, I've already got it up there. I wrote that before and didn't erase it. Okay, sodium hydroxide is because it only produces 1 hydroxyl for each sodium. Right? So if you know the concentration of sodium hydroxide, you automatically know the concentration of hydroxides. But for calcium, for every 1 calcium hydroxide, it produces 2 hydroxides. Right? So the hydroxide concentration is going to be twice that value. 2 times 10 to the minus 3. Right? And that gives you a pH of 2.7. A pOH of 2.7, a pH of 11.3. So it's only slightly more basic than sodium hydroxide at that concentration. Okay, now we've talked about, up to this point, weak acid equilibrium. We can also discuss bases, the K value for a base. Right? So in order to have a K value for a base, you need the, whatever the base happens to be. And in this case, it's the conjugate base of the acid hydrocyanic, right? So it's that one. If we put this one in solution without the proton, okay, how would we do that? You know, pair it up with a sodium ion, right? Sodium cyanide, put that in solution. And that'll give you the cyanide ion without the hydrogens. But the sodium is not going to react with water, right? Because sodium hydroxide is a strong base. The sodium ion is a weak acid. It will not strip a proton off of water. So it won't react with water. So sodium is more or less a spectator. So here we have our cyanide. And I was just showing you how you get cyanide in solution without the hydrogen ions. Now, once it's in there, it's going to react with water, right? Because it comes from a weak acid, that means this is a strong base, right? So it wants that proton, and it's going to get it. So it goes like this, right? And what's left over after you strip a proton off of water? Hydroxyl. Okay, so that's the controlling reaction. Well, that's the reaction we're interested in. We can calculate a Kb value for that one. You just need the aqueous concentration of this one at equilibrium, concentration of this one at equilibrium, and the concentration of this one at equilibrium. And that one doesn't count because it's a pure substance. Okay? So that's the Kb for the cyanide ion. Notice that it's not just flipping the Ka value, right? The Ka would be this one on the bottom and cyanide on the top with hydronium ions. So they're not, you don't just inverse one or the other. They are related, but they're related through their reaction with water, not by direct manipulation of the formula. So here we have the Kw for water. We know how to calculate POH, and we know how to calculate the pH from it. Those are just reminders, right? So in this case, that square is supposed to be a double barbed arrow. So we're going to deal with ammonia in solution. So what are the major species? When ammonia goes into solution, we know that the Kb value for it is this. So it's a base. It accepts a proton from water. So that means this Kb value is appropriate for this expression. We just have to write what the expression is. Right? So the Kb for that expression is going to be the ammonium ion that's produced times the hydroxyl concentration divided by the ammonia concentration. And water doesn't count. And that's equal to 1.8 times 10 to the minus 5 kV. Okay? So, where did we get this expression? Well, if we write out the reaction, then we have initial change in equilibrium for this one also. We know that we started with 2 molar here, that doesn't count. Right? You can ignore the water because it's not going to change at all. We started off with 0 here and here. So the change is going to be, we're going to lose some of this. How much? Well, we're going to lose X. It's going to show up over here. Right? So this is going to be 2 minus X. This is going to be X and X. So 2X is on top, 2 minus X on the bottom. That's where this came from right here. Since it's weak to, 10 to the minus fifth, we can ignore that X. So X squared, these two times each other, divided by 2 equals the KB value. And you can calculate the X, right? So that's the concentration of OH. So we calculate the POH from that and subtract it from 14, and we get 11.7H8 is the pH of this solution. Okay? Now, if that wasn't bad enough, some acids are polyprotic. That is, 2 or more protons are available for dissociation from the acid. Unlike, I'm gonna have to switch again. Let's try blue. Unlike this one, or this one, or this one, or whatever else, HCN that we've talked about, those are all monoprotic. Right? There's only one proton available. Or even if you have other hydrogens in there, those hydrogens are fixed. They cannot be dissociated. That's why we stick this one out here by itself. That says this only has one proton. Acetic acid. Okay? Polyprotic, for example. Sulfuric acid. It's got 2 protons. Or phosphoric acid has 3 protons. I think there are others. Some have 4. They're rare. So these are where we're going to concentrate our efforts. Now, each one of these, let's take the phosphoric because it has 3. So what happens in solution? Well, it can do this. Okay? That's a rule. When polyprotic acids dissociate, they do so 1 proton at a time. You don't get all 3 of them coming off at once. One of them comes off and associates itself with water, makes a hydronium, and leaves you with this one. Now this one can also dissociate. Okay? So we lose 1 proton here, that makes this a minus. This was already a minus, so we lose another proton, makes this one 2 minus. And that one has 1 proton left. It can dissociate some more. Make 3 minus. I'm not going to use blue anymore. I'm not even sure you can see that very well. Not doing much better, is it? I was hoping the combination would give Better recording. Now, each one of these reactions has its own Ka. So we have to say this one's Ka1, this one's Ka2, this one's Ka3. Okay? So this one would be that times that divided by that. Okay? And this one would be this one times this one divided by, oops, 3, 2. Okay, you probably guess what this one's going to be. Okay, so each one of these reactions has its own equilibrium constant. Okay, now H3PO4, phosphoric acid, is a weak acid. In other words, it doesn't dissociate a lot. But it does produce some protons in solution. So it has a K value. And once you've removed a proton from this species and you leave this one, you've got a negative ion here. So it's going to be more difficult to remove a positive ion from that one than it was from the neutral species. Right? So that means that this one is going to be even weaker than that one. And this one is going to be weaker than that one. So what does that mean to the K values? That means as you remove protons, the K gets smaller and smaller and smaller. For each successive removal of a proton, the K gets smaller. Okay? Which also means that in most cases, only this one dominates for production of pH. Right? These are only useful when you're trying to find out what's the concentration of these other species. Right? Because you'll find that with a simple calculation that these guys are just so much smaller than that one, they don't matter. But if you're introducing phosphoric acid into an environment where maybe this reacts with some other, like a metal or something in the solution, then you may need to know how much that there is of that. So it's not, they're not throwaways. But as far as the pH goes, this is the one that matters because it's so much larger K value than the rest of them. And there they are. See, so this one is 5 orders of magnitude smaller, and this one's 5 orders of magnitude smaller than that one. So that just proves our point. The first one is the one that matters for pH. Right? So we calculate the pH, we find out X for a 1 molar solution is 0.0866. Right? We run the 5% rule, we find, we can't make that assumption. We tried the 5% rule and it failed. So what do? Well, you have 2 choices. You can go in, set up your quadratic, don't cancel out that X because it's significant, and solve the quadratic. Or you can take this concentration and plug it into the X values, right? Or plug it into the X value that you had canceled before, and then solve for the other X's. That's called the process of iteration. So you get closer and closer and closer. And for some equilibrium situations, I may have said this before, iteration is the only way, because some equations are not quadratics. They may not even be cubics. They might have fourth, fifth, sixth, seventh order polynomials, in which case that you probably eat up a lot of compute cycles for your mainframe if you try to solve those. So iteration is a more efficient way to do it. So you do it iteration once, check your 5% rule. If you still miss it, it's going to get closer. Try it again with a new value, and then you narrow it down till you get below 5%, and that's your answer. I don't think I'm going to give you guys any of those, because it just takes too long to do it.
Right.
So, well, I say iteration, successive approximations. That's another way of saying iteration in one word, successive approximations in two words. So, like I said, we substitute that value in the X in the denominator, right there, like that, then solve for X again, right? And then check our 5% rule. And there we are. Just that one approximation puts us well below 5%. And we're good to go with that value for X. So now we could calculate the pH. Right? We just take that value and we say negative log of that value is 1.08 pH. Now, these might be weak acids, right? Based on our definition of K, they don't dissociate a lot. 10 to the minus fourth, I think, or third, 10 to the minus third. But that's the intensive property. Capacitive property is, what if you have a huge concentration of this? Well, you won't get as much percent dissociation, but you will get a much higher concentration of hydrogen ions. So phosphoric acid that's weak, that's low concentration, will be weak in terms of its dissociation and weak in terms of its corrosive effect. But a high concentration of this acid will produce enough hydrogen ions to be extremely corrosive. Even though it's a weak acid, it'll produce enough hydrogen ions. You stick your hand in that beaker of concentrated phosphoric acid and you'll know it pretty quick. Okay, so if we're going to calculate the equilibrium concentration of the phosphate ion, this one right here, we got to work our way down through these successes down to here to find out that. All right. So we've already done the 1 molar, and we found out these are our starting concentrations for these two, right? Right here. Wait a minute, H2PO4, yeah, H2PO4. And we know that we're starting out with this one because we determined that value, right? So we determined this one and this one from these positions. And this one is starting out 0. So we're going to subtract some of that, add some of that, and we do another calculation, right? And that gives us X equals, well, as it turns out, these two values, if we let that one go, then this value is gone. It cancels out. So that means X hasn't changed. So once we know that, we can get down to the value, we can get down to this last one here, and then we're targeting this one right here. So we found this one to be approximately true all the way down through this level to that level to this level. Now we can do the calculation, assuming that that one there, and this one will add some of that one. Here we go. How did I get that value? Oh, okay. So the hydrogen ion concentrations now are going to be this one plus that X. So this one plus that X value. Where's our X value? What's the X value? 6.2. I must have had to go backwards more. Here we go. There it is. It's actually equal to the K value, right? If we can say that these approximately are X, then X is equal to this one for this calculation. Did I lose you? Let's go back to this one. This calculation, if we say that one is insignificant, then that reduces this whole expression down to X. So X is actually equal to the Ka. Okay. Now we can go to the next step. And we know that the hydrogen ion concentration that we start with, well, actually that we end with, is this plus the Ka value, Ka2, will give us this value for the hydrogen ion concentration. And that means that the hydrogen ion concentration is here, and HPO4 2- is there. Right, we've determined that one, because that's the one we added in as X earlier. And then this one is our unknown. So then we solve for PO4 3-. We find it this much. It's not very much, very, very small amount. Oh, that was all we had to do, right? Just find that concentration. Okay. So PO4 3- is very, very small. Or even a 1 molar solution. Okay, what are salts? Well, salts have characteristics. They are ionic compounds, right? They dissociate in water. And the individual ions, as they break up, can react with water, right? So they can act like acids or bases. They can produce protons or they can accept protons. It just depends on the nature of the ion. Now, in our actually, the definition of a salt is in terms of acid-base reaction. And for most acid-base reactions, you have this one plus this one. And this is the anion, that's an anion. So they swap places. And this HOH, right? That one and that one makes water. And the AB, written properly, as plus-. That combination of this anion and that cation, that is a salt. That's the definition of a salt. And that's what all common acid-base reactions produce. Like hydrochloric acid and sodium hydroxide. Sodium and chlorine together, table salt. But chemically speaking, a salt is any combination of those, of the cation and anion from an acid-base reaction. All right, so let me get back to my slide now. If you have, we're also interested in when you combine an acid and a base, what will be in qualitative terms, what will be the nature of the solution? Will it be neutral? Will it be acidic? Will it be basic? Well, let's take the easy one first. If you combine a strong acid and a strong base, you always get a neutral solution, right? Because neither one of them wins. Maybe I'm getting ahead of myself. It's close. Okay. So let's take these slides. A basic solution is formed if the anion of the salt is in the conjugate base of a weak acid. So, you know what that means. If the anion of the salt is the conjugate base of a weak acid. We showed one of those a little earlier. Sodium cyanide in solution. So what does it produce? Well, it produces sodium ions, produces cyanide ions, right? So this one reacts with water. Let's see. Reacts with water to produce, if this is a, the anion of the salt of a conjugate base of a weak acid. So that just means this is the weak acid, and the anion, this is weak, this is strong, okay? So that means that if this is a weak acid and that's a strong acid, it's going to strip a proton off of water. So what happens when it does that? Well, it produces this one, the weak acid, plus hydroxyls. That's why it's basic. Because this is a strong base, conjugate base of a weak acid. It strips a proton from water and makes that hydroxyl. That's why when you put a salt of a strong base and a weak acid, so if the base is strong, and this is the a combination of a strong acid and a weak base, that gives you a solution that is basic. And this is why it's basic. Right? Because this cation does not have a strong attraction to hydroxyls. Right? If it did, it would strip a hydroxyl from water and leave you with H+, hydrogen ions. But it doesn't. Because it comes from a strong base, it makes a weak acid. So vice versa, if the base is weak and the acid is strong, then you get an acidic solution. Let's see. I'm trying to think of an example. Combination of a strong acid and a weak base. Ammonium chloride. So this is from a weak base. This is from a strong acid. So when it dissociates, it produces this one plus this one, but this one reacts with water. That one doesn't want a proton, right? It's a weak base, comes from a strong acid. But this one, comes from a weak base. So it combines with water. It takes a hydroxyl from it, right, and leaves proton. So that makes it acidic. Okay, so I showed you this one earlier, I think, when I was talking about calculating pHs and pOHs. Kw is equal to Ka times Kb. there's a conjugate acid. That one makes an acidic solution. Now here's the situation if you have, let's see, cation anion acidic base example. All right, so I'm not sure what I'm trying to say there. Cation's neutral, anion's neutral, acid or basic. This would be strong acid, strong base yields a neutral solution. So this one would be the anion is a conjugate base of a weak acid. Conjugate base of a weak acid. This one. So weak acid, you form the salt from a weak acid and a strong base, you get a basic solution. Right? So there's your rule of thumb. If you got a weak acid and a strong base to produce your salt, then when you dissolve the salt in water, you get a basic solution. Right? So if this comes from a strong base, you get a basic solution. Not for the intuitive way that you would think of it, but for this way. That is the chemistry. But rule of thumb, strong base, weak acid gives you a basic solution. Weak base, strong acid gives you an acidic solution. Now, what if both of them are weak? If both of them are weak, you have to compare the Ka of the acidic origin and the Kb of the basic origin and find out which one dominates. Right? So we would have to look at the Ka of sulfuric acid versus the Kb of aluminum hydroxide. And the one that was the larger value would give us whether it's basic. Right? If this were larger, it would give us a basic solution. If this one was larger, it would give us an acidic solution. Okay, so here we go. If the Ka is greater than the Kb, you get an acidic solution. If the Kb is greater than the Ka, you get a basic solution. So there you go. There are the rules. All right, let's see, what are we doing? 2:30? Let me check it out here. How are we doing? Okay, that's not bad. Do you need a break yet? Okay. We're going to take a short break for our Zoom students, and I'm going to pause the video, and then we'll come back to it in just a few minutes. There we go. All right. So, let's refresh our memory on how to calculate the Kb of the conjugate base of each one of these acids. All right, so the Ka is going to be that and this over this. And that's 1.8 times 10 to the minus 5. But the Kb assumes that you're introducing the conjugate base of that acid into solution without its associated proton. So if it comes from a weak acid, that makes this a strong base. So what's going to happen is this one will react with water and produce the acid plus OH. Now, I know the rule is weak acid makes a strong conjugate base. But what it really means is a weak acid produces a stronger conjugate base than its associated weak acid, which means if the weak acid has a tendency to give up protons at a certain level, its tendency to extract protons is much stronger. Okay, so it's a relative term. So how do we calculate the KB here? Well, if we have all the values, we just need this and that divided by this. But if we don't have the values, then we need this relationship. Ka times Kb equals Kw. And this one is always that one. So if Ka is this one, now we have an equation in one unknown, we can solve it. So the Kb then is going to be for acetic acid. Actually, the Kb for acetic acid is the wrong terminology. The Kb is for the acetate ion. So this would be that one divided by this one, which is, what did I do with it? Here we go. So this is 5.6 times 10 to the minus 10. So what does that mean? That means that the Kb for this reaction prefers this ion. Keep it that way. That's kind of unusual, isn't it? I would have expected. Here we go. But numbers don't lie. How about cyanide? Well, if you use the same procedure for cyanide, all we need to do is take Kw and divide by the Ka for hydrogen cyanide, hydrocyanic acid. And we get 1.6 times 10 to the minus 5th. Okay, so hydrocyanic acid is a weaker acid than acetic acid. So that means its conjugate base should be a stronger conjugate base than the acetate ion. And that's what this says. This is a larger value than that. So that means the conjugate base of this weak acid is stronger than the conjugate base of that weak acid. Okay, now here's a problem for you. Given these different species, one molar solutions of each, arrange them in order of lowest to highest pH. So lowest pH would be more acidic. Highest pH would be the most basic. All right. Our first approach is qualitative. Since we don't need to actually know the numbers, maybe we can reason it out as to what the order is. Well, the way I do it is I nail down the extremes. All right, so which one is going to be the most acidic compound in aqueous solution? Well, let's look for the acids, right? That's not one, neither is that. So we got this one, and this one. Those are acids. So which one is the strongest one? Well, we know that this one is weak, and these are halogens, the hydrides of the halogens. So they should be in the neighborhood of the strongest. But which one is stronger of the HBr, HF? Actually, the acids get stronger as you go down. So this one, hydroiodic acid, is stronger than hydrobromic, stronger than hydrochloric, is stronger than hydrofluoric. So the strongest one in this whole bunch is HBr. So in terms of acidity, that's the strongest. So the other end would be the most basic. Right? So which one's the most basic? Well, it would be a strong base, right? So we would look for one that produces hydroxyl ions. And this is the only one. So this one nails down the other end. This is the least acidic or the most basic. Okay? And then I go for the middle. Are there any in there that are neutral? We look for a salt that's formed from a strong acid and a strong base. And it looks to me like sodium chloride is a good candidate for the middle. So that's neutral. Okay. Now, we've used 3 of them. We've got 5 more to stick in there. So these are the steps that I've followed so far. Strong acid base, well, I did that one. Sodium chloride, so that puts it in the middle. Then we look for strong bases or moderately strong bases. Sodium hydroxide, ammonia is not as strong as sodium hydroxide, but doesn't miss it by much. Okay. Are there any compounds composed of ions from weak acid, strong base interactions? So weak acid, strong base would be a basic solution, wouldn't it? Our rule of thumb. Weak acid, strong base. So there's a weak acid, strong base, sodium cyanide. Let's see. I don't see any others. So that says that sodium cyanide goes here. Okay, are there any acids derived from halogens? Well, we did that one already. HBr and HF. All right. So HBr is stronger than HF. So we put those in that order. So that's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Plug those in so we can accommodate those. Now we've got ammonium chloride and hydrocyanic. All right, so we've still got another acid, HCN. We have to decide the relative position of HCN and ammonium chloride. So this is from a strong acid, weak base, and this is from a weak acid. So which one is which? I mean, which one is more acidic? I would tend to believe this one would be slightly more basic. than this one. That's just a guess. Okay, so that's what we're saying so far, that order. This is the more acidic one. This is the more basic one, and we spread these in between. Now, that's the qualitative way. There is a quantitative way to determine which is which. Look at the Kas and the Kb values. Right? So, this strong acid doesn't have a Ka. Why? Because its Ka would be infinity. Right? If we tried to calculate the Ka for HBr, we'd have H and Br and then HBr. And what's this value? 0. Anything divided by 0 is infinity. Right? So the Ka for a strong acid like HBr has no meaning. So it's definitely at the top of the list for the most acidic. And then sodium hydroxide is a strong base, and for similar reasons, its Kb would have no meaning either. So we got those out of the way. Now the neutral, we stick in the middle, but we got to decide where do the others fall. And if we know the Kas are going to be on the acidic side. Right? So we say that this one, the HF that's a stronger acid, right? It's a larger number than the next one, and that's a larger number than this one. And then we can compare the Kbs, right? So the most basic is going to be the largest number here. Why? Because the Kb produces hydroxyls, right, on the product side. So the larger Kb is going to be the more basic. And this would be the less basic, but not by much. They're very close. Now I wonder, what if we calculated the Kas? Well, the Kas for these would have no meaning, right? We have to use Kbs, right? Because the Ka here would be the same as that value right there. So that would have no meaning whatsoever. So we have to use Kas as far as they go. Once you're past neutral, you have to switch to Kbs. Right? Kas on the acid side, Kbs on the basic side. So what would the K value be for sodium chloride if we were to calculate one? It'd be the same as water. Right? A neutral solution says that water is the only reaction that is significant. So it would have to be 1 times 10 to the minus 14 right here for the Ka. Okay. And that gives us the same order that we determined qualitatively. All right, so let's look at a salt solution and see if we can determine, well, whatever the question is. First question is, what are the major species? If we got a 0.3 molar solution of sodium and fluorine, then what are the major species? Well, that's HF. That's for the Ka. But the major species, we're going to produce sodium and fluoride ion, because this is completely soluble, and water. So those are the major species in our reaction. What are they going to do? Well, sodium fluoride is not a major species because it's completely dissociated. There's none there. So what about the reactions? We're going to look at all of them, no matter how ludicrous they are. So there's fluorine, right? So it could react with water, right? Fluoride and water are major species. So it could react and produce HF and OH minus. That's possible. Water and water react. That's always there. sodium and water producing sodium hydroxide and that's ludicrous. Because sodium doesn't react with water. Sodium comes from a strong base. It's already given up its hydroxyls. It doesn't want them back. It's not going to take them from water. Right? So that one we actually throw out. Sodium and fluoride don't react, right? Because they're already dissociated. So that one's out. That one's out. Now what we have to do is decide which one of these is the dominant one. Which one controls the pH? We look at, notice that this is the conjugate base of HF reacting with water to produce OH minuses. That means what are we going to calculate here? A Kb. And there's our water. There's our Kb, because we know the Ka for hydrofluoric is this, divided into Kw. There's our Kb for this reaction. And of course, water is always Kw, 10 to the minus 14. So for the first reaction is over 1,000 times larger than the Kw. Right? That means this one is going to dominate. That's the one we focus on. All right, so after that little jaunt with logic, we want to look at an actual calculation using cyanide ion in the form of sodium cyanide. Right? So we're given the Ka for hydrocyanic acid, so we know it's simple to produce a Kb for the cyanide ion, right? And the concentration in solution is this, so that's our starting point. First, the major species, sodium, cyanide ion, and water. These are the possible reactions. There's our cyanide reacting with water. There's water with water. Sodium doesn't react with water. Cyanide doesn't react with sodium. Right? So the only two that we're interested in are the top two. Now we got to decide which one is the most important. Right? So we need a Kb for this reaction to show which one. Say when we look for dominant reactions, we want to know which one is driven furthest to the right. Furthest to the right. Because these are our starting species. So we want to know which one goes furthest to the right. And in order to do that, we need the appropriate K value for each one. Well, this one's already given. Kw is 10 to the minus 14. But this one is derived from hydrocyanic acid. And it is in the form of Kb, right? 1.6 times 10 to the minus 5. So the larger K value here for this reaction says it dominates over this one. So here's the reaction that dominates. Once we determine the dominant reaction, then we can do some ice tables. Right? We're going to start off with this concentration of cyanide with none or virtually none of the HCN and OH minus. We're going to lose some cyanide. We're going to produce some hydrocyanic acid and some hydroxyls. And there's our equilibrium situation. Right? So we set it up like that. And to go from here to here, we're saying that X is so small that it doesn't matter. So then when we solve for X, we get that molarity and that pH. POH, excuse me. X is OH concentration. So this is the POH. Let's see, this one goes from here to here, and then this one goes down here to produce the pH. And what we assumed at that point, we didn't calculate it, was that it did satisfy the 5% rule. Okay. Okay, up to now, we've been talking about these equilibrium situations as basically laws, right? This is how it happens. This is how it works. with only a tinge of theory in the background. But there are various models for acids and bases that explain why they behave the way they do. Two of the factors that control acidity in binary compounds is bond polarity. How polar is the bond? What does that mean? For example, hydrochloric acid, right? In solution, the stronger the acid, the more likely the hydrogen is to dissociate. And the more polar the bond, the more likely it is to dissociate. Why? Because the electron density is further removed toward the electronegative cation, anion, excuse me. Right? So if we move electron density this way, that makes this more positive and makes it easier to be removed by a water molecule and form a hydronium. So the higher the polarity of the bond, the more acidic. So for acids, high bond polarity is good for making stronger acids. Bond strength, right? So if we have something that is, let's see. Actually, these two are related. They're measured differently, but they are definitely related. If the bond is more polar, that weakens the bond. So the bond strength here would be lower. Now, this concept is more useful for organic acids because you really are talking about the strength of a connection of a hydrogen ion to its associated, whatever. It might be a carbon, it might be an oxygen, it might be something else in an organic molecule. So the bond strength for acidity, low bond strength is good. And that just means if you have hydrogen attached to something here, then if you've got something else over here that is more polar, it pulls electron density that way and weakens this bond. So you can increase the acidity of that hydrogen simply by replacing that Y with something with stronger polarity. So in a way, polarity and bond strength are related. But high polarity is good for acids. Low bond strength is also good for acids. Okay, here's an example where we're in this family of halogen hydrides dissolved in water, make their acids. And we notice that the bond strength is a very strong bond between H and F, and the bond weakens as you go down. It primarily weakens because the anions get bigger and the charge density is more diffuse, right? So there may be a negative charge on each one of these in theory. They're not necessarily a charge, but a oxidation state. They're all -1 oxidation. Right? But if we spread that oxidation state out over a larger area, it has lower strength. It's an intensity factor. You spread it out, it decreases the intensity of that oxidation state and the ion that would be produced if the hydrogen were lost. So you spread that out, that makes the bond between this anion and the hydrogen much weaker. So it has to do with size. Okay, so what's an oxy acid? An oxy acid has oxygen in it, right? So you got a hydrogen, and it's associated with an oxygen, which is attached to something else, right? So here's an example. Nitric acid. and you have your hydrogen here. Actually, this is going to be 2, 4, 5. I need another one. There. So, what's the effect of oxygen? Well, let's compare this to an analogous form. Right? This is nitric acid, right? HNO3. And this is what? Nitrous acid. Okay, which one's the stronger acid? That one. The rule of thumb is the more oxygens, the stronger the acid, as long as all other things are equal. Right? You have the same nitrogen, you have one hydrogen, and you have a different number of oxygens. Then you can safely say that more oxygens mean stronger acid. And this is definitely a strong acid, but this is a weak acid. Now, why is that? Oxygen is an electronegative atom. It's more electronegative than nitrogen, right? Lower left, upper right, left to right in a period. So oxygen is stronger than nitrogen. Nitrogen does draw some electricity, some electron density away from the hydrogen, but the presence of oxygens attached to the nitrogen add to that pull of electron density. Right? So the more oxygens you have, the stronger the pull of the electron density away from the hydrogen. And there again, the more density that you can spread up here, the less down here, the easier it is for that hydrogen to dissociate. So here, it's not as easy to dissociate compared to that one. Okay? That's what oxygens do. We could say the same thing for this one versus this one. Sulfuric versus sulfurous acid. Same explanation. This is strong, this is weaker. And these are just series, all right? So here's the, this is actually a better example because you have more members of the series. So there's perchloric acid, there's chloric acid, there's chlorous acid, and there's hypochlorous acid. And notice this has a very large, well, I wouldn't even say it has a K value. It's strong acid. It's got 4 oxygens, right? So, you know what? I drew that wrong. There. My apologies. In fact, didn't even have that. Okay, so you get weaker as you remove oxygens, right? So this one is the strongest. This one is reasonably strong, about 1 K value. This one is really weak. There. This one is really weak, and this one's even weaker. Okay. So what does that mean for, let's take that by extension, hypochlorous acid. What if we substitute here instead of that? See, this is a weak acid, right? We substitute sodium in there, derived from a base, strong base, right? Based upon our rules of thumb earlier, strong base, weak acid means basic solution, right? So sodium hypochlorite And if you get it at the store, it'll be 6%. That's bleach. So bleach is going to be basic. In fact, very basic. Because this right here. Okay. In fact, we used to use bleach in certain chemical analyses because we needed to be sure the solution remained basic for the reaction to occur. We just use a little bleach. As long as the hypochlorite and the sodium were not involved in the reaction, we could get away with it. But it would maintain a basic pH and promote the reaction that we were targeting. Okay. For oxy acids that are in a homologous series, they call it. In this case, we've got OH, and the only thing we're changing is the anion. So if we go from chlorine to bromine to iodine, down like this, then we find that the oxy acid is just the opposite of the hydride versions, right? Without the oxygen, HI is a stronger acid than HBr, and which is stronger than HCl. And when you stick an oxygen in there, what you're doing is you're spreading the charge density over a larger atom, and that actually allows more charge density to be delivered toward the bond between the oxygen and the hydrogen, right? So the bond here between oxygen and hydrogen is stronger than it is between this one and that one, which makes the HOI weaker. So the trend is exactly the opposite of the earlier trend we came up with. Now this one, there's virtually no electronegativity involved here. This is methanol, right? Wood alcohol, the kind you can't drink. And its Ka is estimated at 10 to the minus 15. So in one respect, it can be considered an oxy acid, but the bond, the contribution to the bond strength between O and H is virtually nothing. So what that means is for molecules that have OHs in them, organic molecules that have long chain or complex chains of carbons, and they have an alcohol group somewhere on that molecule, it doesn't matter where it is, most of them will have a Ka of that value, no matter how big the carbon chain is. Okay, that's convenient if you know that. Oh, so we didn't put a HOF in that series for the simple reason that it's not stable. In water, it decomposes and actually produces hydrogen peroxide and hydrofluoric acid. So it's virtually impossible to measure the Ka for that one. Okay, now here's another class of compounds. Talked about the oxy acids, right? Now let's talk about the oxides. There are two types of oxides. The acidic oxides, or the acid anhydrides. What does that mean? That means that if you visualize these compounds as being derived from the acidic version, so just imagine a hydrogen out here, maybe two of them. If you just imagine that out there, then you can, this name makes sense, the acid anhydrides. Anhydride, an means not. So we remove the hydride from it, right? So what's left? Well, the oxide is left. Sulfur dioxide, nitrogen dioxide, carbon dioxide. So those are all gases, right? So they really don't have any meaning as acids until you put them in water. So we need to look at the reaction of these in water to deduce their strength, right? So what happens? Well, sulfur dioxide, actually sulfur dioxide is it used to be worse than it is now, a pollutant. And coal-fired power plants were really bad for sulfur dioxide. So they spew this sulfur dioxide out their smokestacks, and it rise up into the stratosphere, combined with water droplets, and produce sulfuric acid, or sulfurous acid, actually, sulfurous acid. Well, when it rained, of course, the raindrops would fall and have that stuff in them. They'd land in lakes, particularly in the Northeast. And they would acidify the lakes, kill everything in there, plant and animal all. So those lakes would be just beautiful blue water and nothing alive. They're coming back now that we cleaned up the sulfur in our. We did it one way is by scrubbing it. You scrub the sulfur out of your smokestacks, or you just burn low sulfur coal. That can be expensive because the steel industry is competing for it. Right? You don't want sulfur in your coke when you're making steel. That weakens the steel. Anyway, so you can do a similar reaction here with NO2 and CO2 and end up with the acid. So that's why we call them acidic oxides. So these oxides, and they're always formed by non-metal oxides, right? So the oxide forms with this one, and this one in our examples, right? So they're all oxides of non-metals. The basic oxides are oxides that form from metal ions, like potassium and calcium, sodium. Those oxides, when they react in water, they produce basic solutions, right? Here's what they look like. So there's K2O, dissolved in water, produces potassium hydroxide. There's your base. So those are basic oxides. So the difference is the basic oxides are formed from metal oxides, and the acidic oxides are formed from non-metal oxides. Okay, now a short discussion of Lewis acids and bases. Lewis found that the Bronsted-Lowry model was not sufficient for some of the reactions that he was studying. And what he found was that the concept of acid-base was a useful one, but limiting yourself to proton transfer also limited the medium in which your reactions occur, right? So they have to be aqueous solutions for the most part, or at least solvents that had the ability to dissociate like water does. But Lewis was carrying on reactions, and some of them were organic reactions, and some organic reactions don't react well with water, right? So you want to carry out those reactions in non-aqueous solvents. And in order to encompass the acid-base concept, Lewis devised this scheme. A Lewis acid is an electron pair acceptor. So let's see what that means. If we say an acid donor in the Bronsted-Lowry is like this, then we look at the acid like that, and what happens? Well, the acid is the electron pair acceptor. So this becomes an acid because it transfers electron pair. Remember, one line, one bond is an electron pair. There's 2 electrons. So it transfers to A and produces a proton. So by that method, we find that the Lewis definition also fits the Bronsted-Lowry definition as well. So it encompasses Bronsted-Lowry, but expands it to include things that you normally would not consider. In this case, we're going to say the aluminum ion comes into contact with water, right? So this is an aqueous solution, and the aluminum ion is a Lewis acid because it's an electron pair acceptor. Right? So it accepts electrons from here. That's the acid. This is the base, and forms this complex ion. This really will only become significant if you go deeper into inorganic chemistry, or you want to get into organic chemistry. Otherwise, you may not see it again. So just learn it well enough to pass the test and go on your merry way. Okay, so here's all of them together. Arrhenius says acids are proton producers, hydroxyl producers for bases. Bronsted-Lowry, hydrogen ion donors, hydrogen ion acceptors for bases. And Lewis said electron pair acceptors were acids and electron pair donors were bases. Okay. So this is just a summary. And we've already covered it in detail, really. You just need to know what the major species are, does the reaction occur, and what equilibrium dominates the solution. What we didn't get into today and will crop up in your review document is situations where it's advantageous to let a reaction go completely to completion. Then take the species there and follow this pattern. So once you have the major species after the reaction is completed, then you actually go backwards into equilibrium territory. Right? So you'll run into some problems like that, and we'll talk about them next week when we do a review. But now we want to get into chapter 15. And while I'm getting ready for that one, let me pause this. Start over again. Okay. Chapter 15 is labeled acid-base equilibrium, but that's what we've been doing in chapter 14. Chapter 15, though, is focused more upon buffers and how they behave. Buffers are extremely important, particularly in aqueous solutions, not just in aqueous solutions, but for living systems, aqueous solutions and buffers are intimately entwined. Without buffers, we would not be able to live. I mean, just look at the circulatory system. Blood is buffered between 7.35 and 7.45 pH. That's a pretty narrow range. If you get much outside of that, either acidic or basic, then you're at your health risk pretty quickly. So, first concept we want to look at is the common ion effect. If we have a system at equilibrium, and we add an ion to that mixture, that is common to the controlling reaction, then there will be a Le Chatelier's shift. So let's try this one. Suppose we have hydrocyanic acid in aqueous solution. It produces some hydroniums and a cyanide ion. Okay, what will happen to the equilibrium if we add sodium cyanide? Well, look for the common ion, right? Is there a sodium anywhere in here? Nope. Not only is there no sodium there, sodium will not react with any of these. Right? So sodium can be discounted. The only one you need to consider is, as far as equilibrium goes, is the common ion cyanide. So addition of cyanide would influence this reaction from this side, driving it back that way. Okay, that's the common ion effect. Okay, what's a buffered solution? Well, in our current context, buffered solutions are related to pH, and a buffered solution resists a change in pH. It doesn't halt a change in pH when you add something to an equilibrium mixture. So if you have what you think is a buffered solution, then one way to tell is to add acid to it or add base to it and see if the pH moves. Right? How much does it move? If it only ticks, like say you have it buffered at 8.4, and you add some acid to it, well, maybe it only changes to 8.35. I say that's a buffered solution. Okay. Now, at the end of chapter 14, I recommended that there were intuited that there were some situations where you need to go completely to let the reaction go to completion, then work your way back in equilibrium. And buffers are a prime example. When you add a strong acid or a base, first you deal with stoichiometry, which means you go as far as it will go, one direction or the other, depending on what you add. Then once you reach that point, you let equilibrium take over, and then it shifts to the equilibrium state. That's when you answer your question.
First ionizes in the aqueous buffer. The acid first ionizes in the aqueous solution. As hydronium ions are added to the buffer, the equilibrium shifts left, according to Le Chatelier's principle. Initially, in this acetic acid acetate buffer, there is a new acetic acid molecule formed for nearly every hydronium added to the solution. As the added hydronium ions react with acetate ions, equilibrium between acetic acid and acetate ions is reestablished. Only a very small amount of acetic acid ionizes to form acetate ions and new hydronium ions. The animation illustrates this process. Here, a hydrogen chloride molecule ionizes in water. The resulting hydronium ion reacts with an acetate ion, forming acetic acid. Due to the small Ka of acetic acid, very few acetic acid molecules ionize to form acetate and hydronium ions.
Why didn't anything happen with those last two bumps? Well, yeah, that's true. But also, the larger molecule is acetic acid. It's a weak acid. It doesn't want to give up a proton. So when it encounters water, it hangs on to its own proton. But that's true. The orientation wasn't right. Let me retake control here.
A buffer solution, like the one on the right, resists changes to pH upon addition of small amounts of acid or base. Each solution here starts at pH 9.25. The solution on the left is not a buffer solution. Click the button to add the strong acid HCl.
Okay. Let's see what happens when we add hydrochloric acid. Whoa. That's more. Oh, yeah. Yeah. Now, what do you think is going to happen to that buffer eventually? Well, based on the fact that what happens to the hydrogen ions when we add it to the buffer, well, what they do is they combine with the ammonia to form ammonium. Okay? So that means that if we keep adding acid, eventually we're going to run out of ammonia. Right? So the buffer doesn't last forever. It's known, the terminology is buffer capacity. How much buffer capacity do you have? You can have a buffer range, but once you've exceeded the capacity, then you're outside that range and the sky's the limit. You know, adding more acid, it just goes, pH drops like a rock. Now I'm going to show you how that works in a minute. I guess I have to retake control. There we go. So, when we have a buffer solution and we add either hydrogen ions or hydroxyl ions, we get a different pH. It's just hasn't changed very much. So, in order to solve the problem, when we add something, first we do the stoichiometry to determine the new concentrations in our buffer solution. Then we let the equilibrium take over and establish a new level place, an equilibrium. And that gives us our new pH. So, if our original ratio is this acid to this conjugate base, then what's going to happen if we add hydroxyls? Well, the hydroxyl is a very strong base. Right? It comes from a weak acid, water. So hydroxyls are going to latch onto protons wherever they can find them. So what happens? When you add a hydroxyl, it takes a hydrogen from the HA and increases the concentration of A minus. So the idea is that you want to have these values large enough so they can absorb more of the OHs. So generally speaking, the higher the concentration of both HA and A minus, the higher the buffer capacity. It'll absorb more hydroxyl or more acid, as the case may be, than it would if you use smaller concentrations. You can still have the same ratio, right? But you have more absolute amounts. That gives you a higher buffer capacity. Now, I'm going to explain that mathematically in just a minute. It has to do with the Henderson-Hasselbalch equation. Okay, so we start off deriving the Henderson-Hasselbalch equation with a weak acid. All right, it dissociates to this and this. Okay? So if we write the K for this one, we find that we have, let's put the H first. We have the H first and the conjugate base together, and then we have the undissociated acid in the denominator. Okay? So look what we can do with this. If we want to find out in a solution, in a buffered solution, what is the pH, right? We're aimed at this one right here. So in an equilibrium situation, we want to put this one on one side and everything else on the other side, right? So if we say, put this one over here, that means that Ka times Ha divided by A minus. Okay? Now what we're going to do is solve for pH, which means negative log. Just take the negative log of that entire expression. So the negative log on this side is pH, right? The negative log over here of this one, and what happens when you take the log of a product? You add the log values after you take the log, right? So the negative log of this one minus the negative log of that one. But here's what we want to do. We want to say negative log of this one, and we will also want to take the negative log of this expression. Okay? So far, so good? This is pKa. That's what that means right there. But we don't know what these are going to be. And it's more important for calculation purposes just to leave them like it is. Except that now we've got pH equals pKa minus the log of HA, oops, ahead of myself, HA over A. Okay? But I don't like minuses. Henderson-Hasselbalch didn't like minuses either. So what happens to the log if you just flip those? Changes the sign. So the Henderson-Hasselbalch equation is this one plus log of A minus over HA. Okay, so what that tells you is you're really interested in the ratio of A minus to HA in your equilibrium solution, and you're interested in the pKa of the acid. Okay, once you know those two, you can find out what the pH is for the equilibrium buffer. So what would be, let's see, what would be the ideal pH for a buffer of this acid with that pKa? Well, if you have equal amounts of A minus and HA, then look what happens. If you add hydrogen to your solution, that strong base picks it up and makes HA. But if you have a base, the hydroxyl is a stronger base than the HA is an acid. It really will latch onto that hydrogen ion. So it takes the hydrogen ion, it makes water, which takes it out of the equation, but it also leaves behind A minus. So if you add acid, you're going to shift this ratio slightly toward HA. And if you add base, you're going to slip slightly toward A minus. So this is the derivation of the Henderson-Hasselbalch right there in animation. There you go. Also, what this means is for the same buffer system, for the weak acid, pKa, all you need is the exact same ratio of A minus to HA. The ratio is important. This one to this one. These can be higher concentrations. As long as they're the same ratio, you get the same pH. Okay? The advantage to going higher in concentrations, maintaining that ratio, is that you have a higher buffer capacity. But there are limits. There may be limits in solubility, right? Or in reactions of the A minus with certain other components in your mixture, right? It might form at a certain level, it might form an insoluble compound, and that sort of defeats the purpose. So you're limited there. Also, you're limited in living systems to the what we call the salt index, the osmotic strength of the solution. So if you go too high with these, you could create a hyperosmotic situation around cells, and that would be deadly. So those are considerations. Theoretically, the pH would be the same no matter what the ratio was. As long as the ratio is the same, you get the same pH. But there are other considerations that you have to consider sometimes. Okay. So let's look at an equilibrium problem using buffers. So we want to know what the pH of a buffer solution that's 0.45 molar acetic acid and 0.85 molar sodium acetate. Now, I'm assuming that when they tell us this is an equilibrium situation, and the Ka of acetic is that. If that's true, if that's the equilibrium situation, then this is the HA, and this is the A minus, and we just plug those values into our Henderson-Hasselbalch, and we get the answer. pH is 5.2, 5.02. Right? We just plug those values, this value here, right, 8.5, this value here, down there. And then the negative log of your Ka gives you the pKa. Is that you or me? Okay. So the Henderson-Hasselbalch equation is extremely useful, particularly if you want to design a buffer. I mean, there are recipes for buffers, I mean, volumes and volumes of them. But if you want to design your own, then Henderson-Hasselbalch is a slick way to get there. This doesn't help much. You can look at it later if you want. Most buffers are formed from large concentrations of weak acids and their conjugate bases. So there's your weak acid, there's the conjugate base. So that the hydrogen ions that you add react with the weak base. Actually, that should be the strong base. That's an error. It should say strong conjugate base. Oops, in the wrong one. React with the strong conjugate base. and the OHs react with the weak acid because the OH minus is an extremely strong base. The weak acid doesn't stand a chance. This OH is going to strip the proton off of the weak acid and leave you with the conjugate base of that weak acid. So that's what goes on in a Le Chatelier's scenario for adding acids or adding bases. This is just restating. The ratio is the important part. That ratio determines the pH. Buffering capacity increases as the absolute concentrations or the magnitudes of these terms increase. As long as you maintain the ratio, you have the same pH, but you get more buffering capacity. Optimal buffering occurs when HA is equal to A minus. That's where the pH change is most resistant. Okay. Intuitively, qualitatively, if you've got equal amounts, you know that if hydrogen ions are going to react with this one to produce that one, then it's best to have, well, let's say you don't know whether acids or bases are going to be added. So you have to split the difference. If you know that acids are going to be added, then you want to favor this one, right? You want to have more of that one. If you know the bases are going to be added, you want to have more of that one. But if you don't know, then the optimum pH for any buffering system is where this ratio is 1 to 1. Buffering capacity. I don't think I have any problems in there for this one. Yeah. So I don't think this one is a real big issue. So what does that mean? Well, if we have the Henderson-Hasselbalch equation to deal with, notice that what happens if these are equal? That becomes log of 1, right? So what's the log of 1 equal to? 0, right? Base 10 is equal to something. So by definition, the log of 1 is the power of 10 that equals 1. So the power of 10, when it's 0, that equals 1. So what does that mean? If we choose equal amounts of each one, then this term becomes 0, and under those conditions, the pH equals the pKa. Okay? That's what you guys are going to do next week. You're going to do a titration curve. You're going to find out what the pKa is, no, the pH in the buffer zone, where 1 to 1, and that pH is equal to pKa. So you know the pKa from that titration curve for acetic acid. You can do the anti-log and find out what the Ka is. I'm going to show it to you here in picture form. So what do we do with the titration curve? Let's draw one. Let's say we have pH on this axis, and that's the response to adding strong base to a weak acid. So this is the added base. In our case, it's going to be sodium hydroxide. Okay? So we're going to start out with just the weak acid, right? So our pH is going to be low. So let me think. Scratching my head. 1, 2, 3. I think it's in this range, right here somewhere. So first thing that happens when you have the pure acetic acid, is the pH starts to increase because it's not buffered yet, right? It's just the acid. You only have the HA. You don't have the A minus in significant amounts. So the pH starts to increase fast. But you reach a point where you've got enough now of the A minus so that you can hold the pH relatively constant. That's the buffer zone right there. Right? And right in the middle of that buffer zone is A minus ratio of HA equals 1. Now, when you exceed the capacity, you add more base than you need, you start to go up again. Right? So at this point, the added base equals the amount of acid that you had right in here, right there, halfway up that line. This is known as the equivalence point. Because that's when the base equals the acid, right? You can find out from this, if you know how much base you added, you know how much acid was in there, you know, if that's an unknown. And we did that with citric acid first term, right? So that's nothing too unfamiliar. But eventually you get to the point where adding more base doesn't significantly increase the pH. So the curve flattens out. So that's a typical titration curve for a weak acid, strong base. Now, depending on which weak acid, this right here will move up and down at a different position. And if this is equal to 1, that means this pH, actually it should be higher up. This pH is equal to pKa. Okay? And that's why this ratio is right dead center in the buffer region. Right? The buffer region is there. Now that's not absolutely flat. It's on a slight slope. Right? But it's flat enough so it resists change in pH. Equivalence. Sometimes, stoichiometric point. That's just where the base equals the acid.
Hydrochloric acid is a strong acid that completely dissociates to form H+ and chloride ion in solution. The H+ ion is rapidly sulfated by water, forming the hydronium ion as shown. The hydronium ion reacts with the hydroxide ion from the dissociated strong-based sodium hydroxide to form water. In this neutralization reaction, sodium and chloride are spectator ions that do not participate in the reaction.
So what does that mean? That means that the net ionic equation for an acid-base reaction is this plus this yields that. That's the net ionic equation for every acid-base reaction. Oh, okay. So here's this is a strong acid, strong base, right? And it effectively doesn't have a buffer region. It goes up here, reaches the equivalence point, then flattens out like that. So strong acid, strong base combinations are not buffers.
Oh, sneeze at that, I'm sorry.
You can do what you got to do. Similarly, the titration curve would be reversed. If you started off with a base, you're going to be high. And then as you add acid, it comes back down. So they're kind of like mirror images. So when we have a weak acid and a strong base titration, and this goes for strong acid, weak base titration, you first have the stoichiometric problem. You let the reaction run to completion, then you determine the concentration of the acid remaining and the conjugate base that's formed. Once you do that, then you can treat it as an equilibrium problem. And more often than not, you can use the Henderson-Hasselbalch equation. Once you get past this, then Henderson-Hasselbalch kicks in and makes the rest of it easier. You can use an ice table. It works both ways. Right. So let's consider this one. Let's see, am I going to need that again? No. I can erase that and make room for the rest of it. Okay. So if we mix 0.1 mole of HCN with 0.04 mole of sodium hydroxide in 1 liter of aqueous solution, series of questions. First of all, what are the major species immediately upon mixing? That is, before the reaction. Well, before the reaction, this is a weak acid, so that's going to be the dominant species. This is a strong base, so it's going to have sodium ions and hydroxyl ions and water. So that's before the reaction. Okay. Sodium hydroxide is not a major species because it dissociates instantly upon hitting the water. Hydrogen ions and cyanide ions are not major species at this point because they come from weak acid. So let's see, what reactions could happen? Well, there's water, of course. There's HCN in water, which would produce hydronium and cyanide ions. We know that one's real. What about HCN and OH to produce cyanide and water? That's a possibility, right? Because OH minus is an extremely strong base. It could strip that hydrogen off of there. This one, no. Actually, it goes over here exclusively. So that one is not going to happen. And this one is not going to happen. So 4 and 5 go out quickly. We have to decide which one of these others dominate. How do we decide? Well, one way is to look at the P values, the K values. Well, it didn't give us the information I wanted. This one would have let's see, we'd have to combine K's to get this one. This one, of course, will be the Ka. This would be a Kw, and this would be a combination. What about after the reaction? Well, if we let the reaction go to completion, well, they're saying that this one dominates. Right? This one dominates. And that's probably true. We don't know the values, the K values for each one of these, but look, this is a very weak, a very small K, so most of it is over here, very little over there. This one is a weak acid, so it doesn't dissociate very much. But this one, for every hydroxyl that's produced or added to the reaction, you get a shift to this side, right? Because if this is a weak acid, that makes this a strong base. And a strong base will strip a proton, right? So this is going to be the dominant reaction right here. Okay? So now that we've established the dominant reaction, what are the major species after the reaction occurs? Well, you still have some HCN, right? Because all of this, this is completely consumed, and you have some of this left over, right? That's the whole idea behind the buffer. You'll always have this, and you'll still have the sodium because it's floating around there as a spectator. We can ignore sodium. All right, so that was a test of logic. Now let's see if we can use that to actually determine pH of a solution that's made from mixing 0.2 mole of acetic acid and 0.03 mole of sodium hydroxide in 1 liter of solution. So what are the concentrations to start with? 0.2 molar because it's in 1 liter, and 0.03 molar because it's in 1 liter. So the major species we start with are these, right? That one predominantly. There are possibilities. Those guys are stupid, so we get rid of them. And then we look for this reaction. This one is the one that dominates. And here's how we know, right? So there's the KW for water. There's the Ka for acetic acid, right? And here's the Kb for this reaction. So what this says is acetic acid is a strong proton donor compared to this one. This one means that you have a tendency toward producing acetate ions from the interaction of these two. The major species then become OH and acetic acid and water. Now, this also says that most of it's going to be on this side, right? So that's during an equilibrium situation. How did we get Kb from this one? We divided it into Kw. This one divided into that. Okay? So we know this one is the one that controls the equilibrium situation. So what we have to do is first find out what our concentrations are, right? If we're going to start off with this concentration for acetic acid and this concentration for hydroxyls, we let it go to completion, right? So what does that mean? That means one of them is limiting, right? One of them runs out. So we look at the magnitudes, and obviously this one runs out first because it's 1 to 1. That one's gone. And it leaves us with an equilibrium situation of 0.17 and 0.03. So this is our A minus, or the conjugate base. This is the acid. Now we can plug it into an equilibrium equation. Well, we can use an ice table too, right? And now that we know what our species are, then we can go back to the acid and find out what the equilibrium situation is, right? So here's the original Henderson-Hasselbalch origin equation, where we have this one yields that one and that one. So the ratio of this one to that one is important, these two. So here we have this one, and that one. Plug them into the equation for the Ka. And the Ka for acetic acid is 1.8 times 10 to the minus 5. Right? We drop that X because it's so small. We find the pH is 3.99. That's if you use the ice table as your equilibrium calculation. But if we take that first equation that took us stoichiometric direction, and those values, then we plug those into the Henderson-Hasselbalch, we get the same situation. All we have to do is take the Ka and convert it to pKa. Then we can use the Henderson-Hasselbalch, and that's a lot quicker. But we do have to do the stoichiometric part first. Let the reaction go to completion to determine what our equilibrium concentration should be. Okay. Okay, we'll pause it for a second.
I was gonna say, you can keep on going, should take half a minute.
Let me see how much we got to go. Not too much. I'll pause.
Okay.
So we'll take a polka siesta here. Okay. So let's get back in slideshow mode here. There we go. So if we, in this example, we have 100 milliliters solution of 0.1 molar acetic acid, which has a Ka value of 1.8 times 10 to the minus 5. And we want to calculate the pH of that solution. This actually doesn't require a buffer calculation. This is just simply an equilibrium calculation, right? We've got this acid dissociating into protons and anions. And we start off with 0.1 molar, right here, 0.1 molar, and that 100 milliliters is blue smoke. It doesn't matter. Not for this problem. So you've got this concentration you're starting with 0 here and 0 there, and you're going to lose some of this, produce some of that, because the equilibrium has to shift to the right because there's nothing there. Then your equilibrium situation is this subtracted x and these x's for those two values. And if we assume that x is very small and that our 5% rule is not going to be violated, then we have x squared over 0.1 is equal to this value, and solve for x. Then take the negative log of it, and you have a pH of 2.87. So the pure acetic acid at 0.1 molar concentration is 2.87. That would be, for instance, our starting point on the titration curve. Start down here at this acidic, and as we add base, it creeps up until you reach the buffer zone and flattens out. So that would be our acidic starting point for acetic acid. And you'll be able to see that with a pH meter. There we go. So now, what if we add 100 milliliters of this acetic acid and 50 milliliters of 0.1 molar sodium hydroxide solution? Now we need to know how much of each one, because the addition of this is going to change the concentration of acetic acid, even if there's no base there. Just simply adding the solution will change the concentration. Right? So we're going to start off first with allowing the reaction to go to completion. So what does that mean? That means this acid plus the added base yields this anion plus water. So here's what we start off with, 0.0667 molar. That's because we had 0.1 molar, so let's just do it. So the initial concentration of HC2H3O2 is how many moles of acetic acid? 100 mils equals 10 millimoles of acetic acid. Right. Have we talked about that before? Millimoles? Okay. It's easier to work with. We don't have to change that for liters and then change it back. It's just a mess. And this is that many millimoles and how many milliliters? Well, we've got 100 plus 50, right? So millimoles per milliliter is the same thing as molarity. Right? So 10 divided by 150 is 0.0667. Okay, that's where that value came from. And we do the same thing for the hydroxyls. We calculate how much hydroxyl is being added, and then divided by the total volume, that gives us our initial concentration of hydroxyl. Okay, so that's our starting point. We let the whole thing go to completion, right? So if the ratio is 1 to 1, that means all of this is going to be used up, right? And we'll have this much left over of acetic acid and no hydroxyls, but we will have some of this acetate. Okay, now we can use Henderson-Hasselbalch. There you go. So we calculate the pKa from our Ka, and then we put in the ratio of these two, the conjugate base divided by the acid, and we find out the pH is 4.73. So it's very close to that value of pKa. So we're right in the middle of the zone. And that's what we've assumed before. These are very close together. The ratio is almost 1. So we're in a good buffer zone. Now, what do you do if you don't have a weak acid, but you have a weak base? Okay, so in this solution, we're mixing 100 milliliters of 0.1 molar ammonia, which has a Kb of this value, and 50 milliliters of 0.1 molar ammonium chloride. So there's your conjugate, there's your base, there's your acid. And the controlling reaction is going to be the ammonia reacting with water. Well, this is going to be the stoichiometric reaction. Right. So we let that react with water. It produces this much ammonia. Well, no, actually, we've got this much, the concentration of ammonia starting with this and that, and none of this. So this is going to be a minus X of some amount. This is going to be a plus X of some amount, and plus X here. And these are our equilibrium situation. Now, why didn't we let this go to completion? Instead, it went straight to equilibrium. I can't explain that right yet. Did I miss a slide? Maybe I missed a slide. Okay. We can't say for sure what the stoichiometric reaction is going to be, right? Because this is sitting in here all by itself, and there's plenty of that. So since this is a weak base, we can't say that the reaction is going to go to completion, unfortunately. So what we can say is that we're going to lose some of it, and we're going to end up with some over here for the simple reason that there's no hydroxyl here. So the reaction is driven to the right. Right? We don't have to calculate Q. We know it's going that direction. So that's what we get for our equilibrium expression. And if we plug the values in, here, the KB is equal to this. We're given KB. Then we put these components together, that times that divided by that. We say that this X is very small, okay? And then we determine that X is equal to this value, which is equal to the hydroxyls. POH is that, and the pH is this, based upon 14 minus the POH. So we're saying that this equilibrium situation did not require a stoichiometric component, simply because the ammonia is not going to react to completion no matter what you do. If we've been starting from this side, oh yeah, that hydroxyl, whatever concentration it was, it would have stripped those protons from that ammonium just like that. Then you would have had a stoichiometric followed by an equilibrium. But this one, that can only be an equilibrium situation because this is a weak base. So what would happen if we used Henderson-Hasselbalch? Well, let's see. In order to do that, we need a Ka, don't we? So we have to do a Ka. So there's our pKa, right? There's our Ka, there's our pKa. And then we need to set up the, because the Henderson-Hasselbalch only works with pKa. So we need to know Ka. We also need to know the ratio of this one to that one. So we have to decide which one is the A minus and which one's the HA, right? So we just look, see which one's got more protons, right? That one's got one more proton, so that one goes in the bottom. This one goes on the top. And if we plug in the numbers there, we find 9.56, and that's what we got before. So Henderson-Hasselbalch can work for weak bases too, but you have to juggle it some. You have to know what you're doing, calculate the Ka, and know which one of these goes in with which term. And like I said, the one on the bottom, normally what we'd put on HA on the bottom and A minus on the top, the HA refers to the one with more protons. Okay. What do we calculate here? Calculate the pH of a solution made by mixing 1 liter of 0.5 molar solution of ammonia, which has a Kb value of 1 times 10 to the minus 5, okay, and 0.5 liters of 0.1 molar ammonium chloride solution. And then by adding 0.1 moles of HCl. Okay, so this is a little more complicated. This first part involves calculating the buffer solution. And then this part involves adding some acid to it, right? So you calculate the buffer solution. Where's the pH for the buffer solution on that curve? And then where does it shift when you add that acid? So these are the conditions before. Ammonia concentration is that, right? 0.5 moles, and ammonium concentration is 0.1 moles. Then we can calculate the concentrations. Well, okay. This is a good time to talk about this. We normally think of the ice tables as using only molarities. But sometimes it's more convenient to use absolute amounts to do our additions and subtractions. And that way, once you find out how many moles of each species are, you finally have it in the end, then you can calculate the concentration. You just need to know what's the volume, find the volume. Then you can calculate the concentration. So sometimes it's more convenient to use absolute amounts rather than concentrations. And we're going to use that technique in our next to last lab, where we do equilibrium with complex ions. So you will see that technique again. So where are we starting? Well, this is where we start. We just calculated that moles there and that moles there. And the ammonia is going to be combined with hydrogen ions to yield ammonium. So actually, they're putting the whole thing together in one big smush. So we're starting with this ammonia, we're starting with that ammonium, and we're adding these hydrogen ions. Okay. All right, so I'll go with that. So what happens? Well, we let it go to completion, right? All of these hydrogen ions are used up, right? So now we've used up 0.1 mole, so we have 0.4 mole left over, but we don't have any hydrogen ions left over. But in the process, we've taken that 0.1 mole here, and it's over here now. Well, actually, after the reaction, we started with that much. Now we're adding another 0.1 mole. This would have been better if we had set it up as an ice table, so we could see the change and then the final. But now that we know what our ammonia concentration and ammonium concentrations are, because we divide them by 1.5 liters. Why do we divide by 1.5? There's 1 liter of this solution, and there's this much of that solution. Right. Oh, here's what we're saying. We're adding HCl as a gas, so we're not changing the volume. Okay, that's the trick. We're not changing the volume, so we can use 1.5 liters. If we had put this in as a solution, then we'd have to account for that volume as well. But that simplifies things. Now we know the concentration of ammonia and ammonium here. Now we can use the Henderson-Hasselbalch. We just need the pKa, and it's that. We did that before. And now we can plug these numbers in. So there's the one on the bottom because it's got 1 more proton, and 9.55 is our pH. Okay. So we're coming down to the finish line. 4 to 5. Okay, we're doing good. We should finish just a little bit early. Calculate the pH of a solution at the equivalence point when 100 milliliters of 0.1 molar solution of acetic acid is titrated with 0.1 molar sodium hydroxide solution. Calculate the pH at equivalence. So what do we mean by equivalence? We mean that the amount of acid is equal to the amount of base. So if we have 100 milliliters of 0.1 molar acetic acid, and we're going to use 0.1 molar sodium hydroxide, they will be equivalent when you use exactly 100 milliliters of sodium hydroxide. They're the same concentration. One's monoprotic and one's monohydroxyl, right? So they're producing equal amounts of hydrogen ions and hydroxyl ions. So since they're the same concentration, you're going to have exactly the same amount of sodium hydroxide added. And the total volume is going to be 0.2 liters once we reach that point. Okay, so before the reaction occurs, both of the concentrations are going to be 0.1 mole divided by 0.2 liters or 0.05 molar. So before the reaction, we're starting with 0.05 molar of both. Right? That's why this says 0.05 molar. Right? So we're adding equal volumes of equal concentrations. We just cut them in half. 0.05, 0.05. So that's where our starting point, where we've got acetic acid plus the base. So here's what we start with. There. Put them together. The equilibrium situation we reach is at a point where we have none of this left and none of that left. We only have the acetate ion at 0.05 molar. Okay. Now what happens? At this point, we've got that acetate ion. It can react with water. So what does it do with water? Acetic acid is a weak acid, so the conjugate base is going to be relatively strong, and it's going to react with water and strip a proton from water. So we're starting off with this concentration. We're going to lose some of it as it removes a proton and produces acetic acid and hydroxyl. So this is the, before change, this is the equilibrium situation actually right here. But we don't have a Ka here, we have a Kb. So if we calculate the Kb from the Ka, that is Kw divided by Ka equals Kb. So there's the Kb for the acetate ion. And this is about the formula for the equilibrium situation for Kb. Then that one times that one divided by this one. We get rid of the x, say this one. So x is equal to that one times that one, then take the square root. And then the POH is this value because x is OH minus, right? 528. And the pH is 14 minus that. So we're actually at a pH of 8.72 at the equivalence point. So when it goes this and that, that's at a pH of 8.72. Okay, at the equivalence point. Now, why do we need to know that? Well, we're going to talk about it in just a minute, but once you know the pH at which equivalence occurs, then you know where that equivalence is going to occur every time. So if you have an assay that you're running and you need to find out how much acid is in there, then all you need to do is titrate straight to 8.72 and read the volume off of your sodium hydroxide. Then you can calculate how much acetic acid was in there. Okay. The other thing you can do is if you can find a color indicator that changes color in the neighborhood of 8.72, you don't even need a pH meter now. As long as the color indicator changes pH in this range, then you can add base until you get that color change. Then you can read the volume off your base and calculate how much acid. Right? So once you've done the preliminary work and found out where that occurs, then you can pick an indicator that will change at the proper place. So that's the equivalence point, just below 9. And these are comparisons of titration curves. Like, so if the Ka is, if you have a relatively strong acid, relatively speaking to the others, then its titration curve is going to be somewhat iffy for use as a buffer. Right? See, that's it could be forced to work, but it would be real test. But once you get up here, 10 to the minus 4, 10 to the minus 6, 10 to the minus 8, right in that region, then you get a distinct flattened region right here. And those work best for buffers. Okay, so this equivalence point is a quantitative value. In other words, if you do the titration, you know exactly where the equivalence point is. If you're using an indicator, this is known as an end point. So the end point just means that's when the titration's over. It's ended. but it's based upon the equivalence point. And it only has to approximate. The percent error, if you say you use phenolphthalein, then it's going to change color up in this region. But that's not bad. Your percent error is going to be very low. Why? Because the difference that you're looking at is linear, whereas the change in pH is logarithmic. So the logarithmic change, while very large, only represents a small linear change. Okay. So about indicators. How does an indicator work? An indicator changes color in a specific pH range. Sometimes it changes color several times, depending on the pH. So some indicators can be used for this pH range, or you could use that same indicator for a different pH range. But the reaction that occurs in your vessel, the reaction that between your acid and base, is also causing a reaction in the indicator. Right? So it's a simultaneous reaction, only there's just a very small amount of it, so it does not have a significant influence upon your overall reaction. What you're interested in is and most indicators are weak acids. So you're going to have the weak acid dissociating into a proton and a conjugate base, and there's a color difference. This particular one indicated is for phenolphthalein. Right? So when the solution is acidic, what does that mean? It has lots of protons. So it's pumping, there's lots of protons in there, and that drives the reaction back here to this one, which means the solution is going to be colorless. But when you've used up those protons, then that drives the reaction in this direction, and once you reach a certain point, the dominant color of this ion minus, the indicator minus, the phenolphthalein, is pink. So in basic situations, you get a pink color. Now, we can calculate the pKa. Right, the Ka is this value, the pK is 9.4. And the, let's see, here's the next slide. Here we go. So here's where we have to take human physiology into account. You know, how does the human eye work? The human eye, while it's a marvelous instrument, can only detect a change in concentration based on this color, can only see a difference in color if the change occurring is about a 10-to-1 ratio. Right? So in order to see a pink color, you've got to have 10 times as much of the ion minus as you do the HIN. Right? So this ratio determines the pH at which you can see that color change. Right? So we plug those values in. Right? If you've got 10 times as many of these as you do those, then we can detect it. So we plug those values in, and that means that for one direction, for the pink direction, you need a pKa plus 1, and for the colorless direction, you need a pKa minus 1 because of the logarithmic effect, right? The log of 10 is 1, and the log of 1/10 is minus 1. So the range that you're looking for is pKa plus 1 or minus 1. For your indicator. And we have charts, right? It's hard to see this one, but you can see the ranges where you see color changes, right? Some of them, and this is more or less a rule of thumb, right? Some you can see at lower differences in concentration. Right? Some it takes a little more. So So here's the pH at which these colors change. And let's see, phenolphthalein should be right about here. There it is. All right. Say if your reaction, the equivalence point is at a pH of 4, you might want to use methyl orange instead. Okay? And that's that, as they say. Now, let me see. Let me turn this thing off. Stop the recording.